Hello students. So this video lecture is prepared for heat transfer subject and the unit is 3, that is known as the radiation. In previous lecture we have discussed about radiation, then some terms like absorptivity, reflectivity, transmittivity, and we define the black body. In today's lecture we will discuss about monochromatic emissive power, then laws of some black body radiation, heat transfer by radiation, and if the time permit we will discuss the remaining part of this content. So here we will discuss first monochromatic and total emissive power. So monochromatic emissive power is nothing but it is defined as the radiant energy emitted by or from a body per unit area, per unit time, per unit wavelength about the wavelength lambda. So if we define that emissive power for monochromatic, so monochromatic, this word describe the or used for single wavelength. So if we measure the emissive power of the single wavelength, any single wavelength, that is called monochromatic emissive power, and it is denoted as E lambda, and it has unit watt per meter square micron. Okay, so this is called a monochromatic emissive power. So here this graph is plotted between E lambda versus lambda. So here this is the one, we can say the wavelength. So the power, emissive power of this wavelength is monochromatic emissive power, and the total emissive power is nothing but it is the total quantity of the radiant energy of all wavelength emitted by a body per unit area per unit time, and it is denoted by letter E, and it has unit watt per meter square. So total, that means any surface can be emit the wavelength from 0 to infinity. So this may be 0 to infinity, means it is having different microns wavelength. So if we specify the emissive power for a particular wavelength, it is called a monochromatic, and if you specify the total energy, radiant energy emitted by that body, is called total emissive power. So in this total emissive power we have having different types of wavelengths, that means it is varies from 0 to infinity. So that is called a total. So it is denoted by E. So how that total is found? By integration of E lambda d lambda from 0 to infinity, we can find the value of E, that means total emissive power. So this is the total emissive power, and if we calculate the emissive power for any particular wavelength, suppose this is the wavelength, any wavelength, that is called a monochromatic emissive power. So these two terms are important for the next derivation, which is called a Kirchhoff's law. So from here we are going to derive the different laws of black body radiation. So first we discuss what is meant by Kirchhoff's law, or derive the Kirchhoff's law. So for that purpose we have to take this experimental setup. So consider that the two bodies are kept in a furnace held at a constant temperature T Kelvin. So this enclosure is called a furnace. Assume that two bodies, out of that two bodies, one body is the black body and another is the non-black body. That is the body having a value less than 1. So this is non-black body, this is black body, and both body will eventually attain the temperature T Kelvin. So this is the, we can say, the constant temperature attained by that particular the two bodies, and also the bodies neither become hotter nor cooler than the furnace. So the furnace temperature is also equal to T Kelvin. That means any temperature, we can say 300, 400 Kelvin. So all these three means this and furnace is attended constant temperatures. So that condition is called a thermal equilibrium. So what is meant by thermal equilibrium? When this body, black body, then non-black body, and the furnace attain the temperature constant, that is T Kelvin, maybe 300, maybe 400, that is called a thermal equilibrium. That means this temperature, this temperature, this temperature, and this temperature, all these temperatures are same. So this is called a thermal equilibrium. And at this thermal equilibrium, each body absorb and emit the thermal energy at the same rate. So when the thermal equilibrium is attained, the absorption and emission of that thermal radiation is at the same rate. But the rate of absorption and emission of the black body will be different from the non-black body. We know that this black body absorb higher energy and also emit higher energy than the non-black body. So for this case, we are going to derive the equation that is called a Kirchhoff's equation or Kirchhoff's law. So let the area of non-black body and black body is be A1 and A2. So this area is A1, this area is A2. Let the I, capital I, be the rate at which radiation falling on the bodies per unit area, and E1 and EB is the emissive power. That means this total emissive power that we have already discussed here. This total emissive power for these two bodies is called as a E1 for non-black body and EB for black body. That means for this E1 and it is called EB for black body. Then at thermal equilibrium, the absorption and emission rates are equal. So we can write I, that is rate at which radiation falling on this body, multiply by A1. So A1 is the absorptivity of the non-black body. Then this capital A1 is the area of that non-black body, is equal to A1 E1. So here also we have to multiply by area A1 and E1. E1 is the total emissive power. That means absorption is equal to emission rate. So here the A1 get cancelled and we are obtaining A1 is equal to E1. Similarly, we can write for the non-black body IAB A2. So AB is the absorptivity of the black body and A2 is the area, which is equal to the A2 into EB. So this absorption rate is equal to emission rate. So similarly, we can here cancel that A2. Okay. And from this equation, that means this equation is called 4.4 and this equation is called 4.6. So we can write E1 upon A1 is equal to EB upon AB. So if we take this side and take this side, so this side is become equal. Therefore, this side also is become equal. So we can write E1, capital E1 by A1 is equal to EB by AB. Then if we introduce the second non-black body, so here if we again introduce another body, which is also called a non-black body, then we can write same equations, that A3 means area of that non-black body and A2 means absorptivity of that third body, which is non-black body. So here also this absorption rate and emission rate is equal. So again we have to cancel these A3 and we can write IA2 is equal to E2. So this is equation number 4.9. Then combine with equation 4.7 and 4.10, 4.4, 4.6 and 4.9, we get this equation. Means this equation we have to combine with this equation and we get E1 upon A1 is equal to E2 upon A2 is equal to EB upon AB, and all this equal to EB. So this is equal to EB because this AB is nothing but it is having value 1 because this is applicable for black body. So here instead of AB we can write 1. So anything divided by 1 is equal to EB. So from this equation or this equation is, we can say, the final equation of Kirchhoff's law, and from that equation we can give the statement of Kirchhoff's law. So it states that at thermal equilibrium the ratio of total emissive power to the absorptivity is the same for all bodies, and equation 4.10 is called a mathematical statement of Kirchhoff's body. So thermal equilibrium, emission rate and absorption rate is equal for all bodies. It may be black body, it may be non-black body. So this is the statement 1. Then there is another statement, or we can say another small derivation. So here we have to use the definition emissivity. So in what is meant by emissivity? Ratio of total emissive power E, capital E, of the body to that black body at the same temperature. Suppose if we take this type of a body, which is a non-black body, so emission rate is E, and at same temperature we take the black body, so that emission rate is EB. So emissivity is equal to E upon EB. So you have to just take the ratio of these energies. So we have already know that E by A is constant for all body. So we can write E by A is equal to EB upon AB. And we know that E is equal to E upon EB. So we can write E is equal to A upon AB. Okay. So rearrange this equation. And we know that AB is equal to 1, which is for black body. So E is equal to A. So these quantities become 1. Then therefore E is equal to A. So from this, again we can state the another statement of the Kirchhoff's law. When any body is in thermal equilibrium with its surrounding, its emissivity and absorptivity are equal. So this equation is also called a, or we can say, another statement of a Kirchhoff's law. Okay. So in this way we have derived the Kirchhoff's law from these two equations. So here we are having first equation, and from that equation we are again define emissivity, and if we put that value of emissivity with the previous equation, we get this equation, E is equal to A. Note that this emissivity and emissive power, both things are different, because emissive power is nothing but this is called a emissive power, total radiant energy of a body per unit time, per unit time, and this small e is another quantity. So here it is the ratio, here it is not the ratio, this quantity is not the ratio, okay, but here that is the ratio. So this emissivity term we can use for the calculation of radiation heat transfer. So emissivity, small e and small capital E, both things are different. That is called a total emissive power, and this is called a emissivity. So it is the actually ratio. So same temperature you have to take the, if you measure the emissive power of these two bodies and equate that, we get the emissivity. That means we are having some value like 0.8, 0.9. So this emissivity can be, we can find this emissivity by experimental method. So for different material, the emissivity is different. For example, we can say for some metal part, the emissivity may be equal to 0.8, 0.9, like that. So in this way we can define the emissivity. So these two statements are important, and it is called a Kirchhoff's law. So here we have completed this part. The remaining part we will discuss in next lecture.